welcome back to Just Africa. Very, very interesting conversations we're going to be having with very, very interesting guests. I've been looking forward to this conversation with Professor Olufemi Adetunji, who is the head of Department Industrial and Systems Engineering at the University of Pretoria. Welcome, Professor Adetunji. How are you doing, sir?
I'm very fine. Thank you so much, sir. Thank you for having me.
But Adi, you've been doing systems management for a long time. Please tell us, what are the lags that you've noticed that the African space has?
Yeah, I think the first thing, maybe the best place going to start is to probably put it forward that I don't even think most people understand the benefits industrial engineering brings to the table when it comes to managing production systems. Okay. Because it's one field of engineering that most people seem not to understand. Sometimes, some people will think we industrial engineers are like maybe artistic designers. Some will think, maybe industrial engineers are the ones that are involved in areas like welding and screwing. So, and it's difficult. So it's one of the first things I would try to probably just explain to people that when you talk to productivity at micro level, that's actually where there are very few fields that will probably make industrial engineering better. You see, when we have students visiting our school to talk about different engineering fields, I tend to be able to say, okay, because what industrial engineers do is not what you see outside. That I know when many other engineers come up, the mechanical engineers will quickly say, we are the ones that make cars. And the electrical engineers will quickly say, no, we are the ones that make your television and all those things. So I often tell them that, no, that is not how engineering works. Especially when students come from secondary school coming for career fair and all those things, that no engineering field makes a thing. Engineers have to work in teams. When you look at the manufacturing environment, when you look at a car today, will you call a car in today's world an electrical machine or a mechanical machine? I say it's difficult because we probably have more electronic parts today in cars and electrical components than even some mechanical components in some instances. So it's difficult to say but when you look at what different fields of engineers do, industrial engineers work with design of processes. Traditionally, if you look at the history of how we started, industrial engineers are typically called productivity engineers then. Okay. Because if you look at the history of those that started industrial engineering, many of them didn't start out to be what they call industrial engineering today. The person considered to be the father of industrial engineering historically is Frederick Taylor, who happened to be a mechanical engineer. But if you start from the industrial engineering is one of the fields that started after industrial revolution, the first industrial revolution. And the key highlight of the first industrial revolution is that humans understand the potential of heat and how to get work out of heat. Because it is from that understanding that what we call engine systems was built for the first time. Yeah. And that is the foundational law of what we call thermodynamics today, that we could actually get work out of heat. And it's on that subsequent things were done. So when you see the idea of creating steam engine, which although interestingly is not steam that is the main thing that actually is used in the system, into what we call locomotives and all of them today, they are built around engines that are made from heat systems that can be converted into work. But what comes with that industrial revolution is the fact that traditionally you need a lot more human beings to work than you actually will need in a system like that. Because what you need maybe horses or humans to do, you can make machines to do multiple folds of that without needing such human or muscles of human or horses. And from that time, we realized that people can farm in large scale, much more than what used to be before that era, where you need a lot of people. In fact, there is a place where somebody will be laughing and say maybe that was why slave trade was necessary and why slave trade was no longer necessary. Because with the machines, you don't need so much slaves to do many of those things anymore. Because machines can do everything. Because machines can do everything. But what happens is, as human beings solve one problem, another problem will crop up immediately. Once you start solving the problem of needing human muscles and maybe the muscles of horses and oxen to plow and grow, you realize that to manage production at that level, at that scale, where machines can just make so much of it, you start realizing you need a different paradigm of thinking. So, and that weaves into every area of the industry, including production, agriculture, transportation, and everything, until when we start moving on to what we call the second industrial revolution, where electricity came, telephone system came, and many things came, and then the society was designed in a different way. You could manufacturing in a place and maybe selling or using the products in a much further place away from where you manufacture. We need a different way to plan all those things. And that was what led to industrial engineering. In fact, at the same time, many disciplines like managing projects, having better accounting system, all of them came at about the same time, that we realized we need to manage many of these things we are making at a large scale. So that was actually where most people trace the genesis of industrial engineering to. A good example of what was always cited was the work of Frederick Taylor, who, while he was in the Bethlehem Steel in the United States, was looking at how people were moving iron ingots and many of those things and coal in the manufacturing process. And he was looking at people coming with different sizes of shovel to move things. And he was asking himself that actually, can the productivity of these people be affected by the size of shovel they are using? Think about it this way. Some people will come with very big shovel. What will a big shovel do? You can carry a lot at a time, but you cannot carry it too frequently.
Okay, yeah.
Then some people will come with smaller shovels. You can carry it very frequently because it's not heavy, but you cannot carry a lot at a time.
Yes.
But what you need is not the size. What you need is the volume that you are able to move. And that was a very smart observation. And he was saying, okay, is there a particular shovel size that makes the volume people were going to carry to be actually the biggest at the end of the day? Because if you come with big shovel, at a sweep, you will carry a lot, but you can't go through many laps. It's too heavy. If you come with small shovels, you can go through many laps, but you're really not carrying much. You're not carrying anything. Yeah. Is there a particular size that when we make people use this size, overall, at the end of the day, they would have carried a lot more? And that was where he started. And he realized about 21 pound size of shovel, when he started experimenting with all those combinations, that the production of Bethlehem Steel, according to some record, more than doubled. In some instances, some records will say almost 4 times. And this is one interesting thing. The people that were carrying the steel, the coal and the iron ingot, they have not changed. The environment under which they are working has not changed. Simply by changing the size of shovel, productivity was more like 2 to 4 times. And that was a very interesting observation. Wow. Simply by changing some few parameters in the production system, we can make a lot more. And think about it. A product like steel, in most environments, except in recent times where you can have a way of creating different types of steel, you basically, from a product like steel, which we call a commodity, you don't make so much money by branding, differentiation. You make a lot more money from volume. So if a company can actually have double or quadruple their output, you can imagine that company will be a lot better, richer, more resilient, more prepared for the future than all the ones around them. They have capacity to probably buy all the others over. And that was exactly what happened. So that became the foundation of many things that we do in industrial engineering today. Because when we talk about optimization, we are saying, is there a particular value of an item or a variable that gives us the best results in the system? That's the summary of what we call optimization. So essentially, industrial engineers are system optimizers. That is there a best way to design this production? Maybe when you are buying something, is there a best quantity to buy? When you are scheduling job, is there a best sequence to follow? When you need to determine the order of job processing, is there a best order or sequence? And many things. When you are laying out a production system, is there a best layout that is where the idea of what we call optimization comes. Because we're saying, okay, if you keep every other parameters constant, can you find out a way to structure this thing in such a way that the output can be made better? And that's what industrial engineers do through various techniques like use of mathematics, use of what we call process physics, and many of those things to create systems that, even with the resources you have, we can get a lot more out of the system.
All right, Prof. Thank you so much. In fact, you have given us a very deep understanding of industrial engineering. Now, coming back to this topic, talking about operational efficiency, how important is this to manufacturers for us to be able to compete on the global stage? I love the analogy of the shovel. You don't have to carry a bigger shovel. So that is like what we are saying now is that you have to work smarter and not harder. But we need to understand the importance of this operational efficiency in the manufacturing industry.
Okay, thank you. Let me start by working harder and not smarter. We are working smarter and not harder. I actually tell people tell my students, you need to work smarter and work harder because the world has become super competitive.
Okay.
So, but this is the issue. If you are working harder but not smarter, you are just going to be frustrated because you will see people that are smarter and are not working as hard as you, and they will keep doing better than you. So, but when you are able to first work smarter, then you can determine the level of hard work you want to do. Because if you are just working hard in a way that is not structured, you would have done a lot, but you will still get nothing. You will still be out of the market. It's frustration. So, I am not saying we will always work very hard, but I'm saying if somebody can work very smart, but work hard while you are smart, you get a lot more out than every other person. Maybe I should just start from there. You know what? One slang we use often in my school is we will say, well, the reason why you have industrial engineering is because many times common sense is not very common. We only call it common sense.
Yeah.
So, when you study something, you realize that, why didn't I see it that way all the while? Yeah. Let me go back to manufacturing. You see, I like telling stories rather than writing equations. Okay. Especially if I'm talking to people that are not in my field, because that creates a lot more sense. Like when I gave an example of the shovel, there are underpinning mathematics that we can develop from that, because most of the things we do in optimization is balancing what we call a number of conflicting functions by choosing an appropriate, what we call decision variables. There are some decision variables that will tie some of those mathematical functions together. For instance, let me give an example. Even from the shovel's case, and I will come back to manufacturing. The issue is there are two functions that are at loggerhead. The frequency of moving of your stock and the size you are moving at a time. As you are moving large size at a time, the frequency is decreasing. As you are moving more frequently, the size is decreasing. So we have contradiction. Somebody that wants to move a lot at a time has to move more slowly. Somebody that wants to move very frequently has to move less size. Those two are contradictory. Then, usually, when you reduce that to mathematical function, you will find there is always what we call a turning point. There is a point where one cost function will dominate the other. Now, if you move too far away from where one dominates the other, you go to the extreme side where the other one now dominates very well. There is always a sweet spot where the two of them appear to cancel each other out. That is what we look for with mathematical function. And when the person first did the experiment, he didn't use mathematics, but that there is an underlying mathematics there that today we know and we can model. And that idea gets translated into so many other areas. Whether you are ordering stock, you are scheduling job, you are laying out production floor, there are always these costs that when you increase that variable, it makes one cost increase and it makes another one decrease. Think about it this way: if you are building, let's say, a storage for what you are going to sell. If you build very big storage systems, now it means you will need less transport.
Okay.
But if you build a small storage system, you will be exhausting the storage quickly. You will need to
Yes.
drive much more.
Yes.
There is cost of driving, there is cost of keeping stock in the storage. Now, you see, those two costs are contradictory. As you increase the volume, cost of keeping will go up, cost of driving will go down. As we decrease the volume, cost of driving will go up, cost of keeping stock will go down. So there must be a spot where there is the best thing. That's actually where the logic of mathematics comes in beautifully. Because we can now put all these things in models and see, we can locate that point and tell you this is the exact size you should build. Every other person that moves below or above it will pay much more than you do.
But
and that's the same thing when it comes to manufacturing. Yes, I'm listening.
Yes, Prof. Do you think that manufacturers understand the link between efficiency, operational efficiency, and profitability?
That's a good question. Everybody uses the slang, but not everybody understands the underlying physics. That's the issue. Let me say it this way. If I bring it away from industrial engineering to mechanics, we all know that when we jump out of the window, we are going down. But not everybody understands gravity. Does that make sense?
Yeah. Yes.
So there are things we can see, but there is a different way to understand what is actually making it to be like that.
Yeah.
Because once you jump out of the window, what happens is gravity kicks in. Gravity acts down the earth and the earth pulls you towards itself. So people that understand how that works can now make calculation. At what speed will you go? What can we do to make sure you don't crash? How do we create maybe something that can float based on some other natural things like air? And we can create many things that can make you land gently. Now, it's still the same environment, but we are using the law of nature to design systems that can now, it will be like you are the master of what nature has. That's what engineering is about in general. It's the same thing when you see what happens in manufacturing. Everybody knows we need to be productive. Everybody knows they will say, in fact, that optimization is a word that everybody throws around. We have an optimal system. We have great optimization, but that actually in our own world where we actually do optimization, we will tell people, be careful how you use that word, except you really know what it means. Because every manufacturer knows actually that we need to find a scientific way of managing this thing. But the issue is how many people actually understand that underlying what we call process physics. So, and those comes in many ways. When you talk about manufacturing, for instance, there are so many things that once you make a decision, other things are consequential. It's like when I talked about jumping out of the window.
Yeah.
The only decision you can make is, should I jump out of the window or not? And from what level should I jump out of the window? Once you jump, the process is out of your control. Nature takes effect. It's the same thing with production systems. There are some decisions that you can make. We call them control decisions or control variables. There are some that they are out of your control. Once you make that decision, the process kicks in on its own. So you live with the consequence. So that's what happens when you are now making decisions that we say, okay, what are the control parameters I have here? What are the things I can fine tune to achieve this level of goal I want to do? And those are things you now study through what we call process design. So I believe most manufacturers know that they need to be able to do better. But the question is, how many manufacturers know what they need to do to achieve that goal? That's where the question is.
Okay,
I hope I answered
Prof, I would have loved you to answer that question right away. What do you think African manufacturers need to do to help us be competitive enough on the global stage? What are those things you think manufacturers are overlooking?
Okay, there are so many things that will be tied together to say this is how we can be competitive in terms of our manufacturing system. Number one, there are environmental issues.
Okay.
Those ones might be beyond even the control of the manufacturer. For instance, there are global environmental issues. The demand structure in the environment, the global policy driven by many countries that are together in the world.
Okay.
For instance, when one country introduces a tariff policy, it affects everybody. It affects demand. It affects many things. How do we respond? Those are policies that might not be within the control of the manufacturers. Yes. Then there are natural factors. Those are macro factors. The government is probably can support the environment in which manufacturers operate through production of basic, what we call manufacturing essentials. In logistics, some of those things are identified to be number one, energy. How does the government make energy available to those people? It affects the overall cost that the manufacturers will incur. Number two is transport. How efficient is the transport system of the country? That has nothing to do with the manufacturer. It will affect them, but they are not the cause. If you have bad roads, it will affect your this thing, but that's outside your control. Another one might be communication. How connected is the country in terms of communication network? At what cost is it made available? All those things filter back into production system, but they are out of the control of the manufacturer. Another one, for instance, is like we can keep mentioning, there are a few of them. Another one is the cost of fund. For instance, let me give you a way to explain this in a practical way. If you are in Japan and you have to borrow money at, let's say, 5% or maybe 0.5%, 1%, 1.5 or 2%.
Yeah.
Or maybe you are in America, you have to borrow at about maybe 3-5%. And maybe you are in South Africa, you have to borrow at maybe about 10%. And you are in Nigeria, you have to borrow at about, let's say, 15-20%. Can you see what it means?
Yeah.
It means if I have my manufacturing company in America, all other things being equal, if we all both run our company exactly the same way, for me to be able to be more successful than you, if you can borrow fund at 5% and I have to borrow at 20%,
yeah.
I must have made much more profit to cover that cost before I can say I can compete with you. I don't know if that makes sense.
Yes,
so that is only from the cost of fund. When you now look at the transport infrastructure, if there is road and everything working here, and I realize that this makes me to be able to need to pay a lot more. So that means I have to also be super productive to cover what advantage you have had because of your macro environment. All those things militate against African manufacturers because the government in most African countries have not given the manufacturers the environment that can make them to compete. That is one level of competitiveness that I say. All those are completely outside the control of this manufacturer. The ones that are within the control of the manufacturers now involve the ones I was talking about. What are your procurement policies? What are your manufacturing decision policies? What are your job scheduling policies? What are your inventory management policies? What are your labor management policies? All those ones are within their control. So it takes all of this together to determine how productive and how profitable and to an extent productive those companies are. So when we talk about being competitive at a global scale, there are things that belong to the domain of the government of Africa. There are things that belong to the domain of people that are manufacturing. We have to look at all of them in an integrated manner. So sometimes the companies in Africa might have even done much better than some of their peers. Particularly because you might have had an advantage in terms of labor costs. But by the time you factor in all this other macro environment, they might still be uncompetitive.
Prof, I was reading somewhere and I read something about flow control. I thought maybe it means you managing, but maybe you would explain from your own experience what flow control techniques mean and then how they can help, improve manufacturing supplies.
Okay, let me explain when it comes to manufacturing systems, what essentially goes through a manufacturing system are materials or products that flow through.
Mm-hmm.
Now, when we talk about physics of process, there are some issues that we call variations or variability in process. Some we have control over, some we don't have control over. Somebody manufacturing a process needs to understand one of the core areas we call variations because, for instance, every resource we are using to manufacture has capacity. Okay. Now, what those capacity do is the rate at which they produce creates flow of materials. When we start introducing our operations work, we say everything you have in a production environment can be categorized into two main categories. Number one, you have resources that we call transformed resources. You have resources that we call transforming resources. And that's what you see in every system, whether you are manufacturing goods or you are offering services. If you look at someone manufacturing goods, example is if you are manufacturing car, you're going to have vehicles that you are making. Those are your transformed resource. Okay. You get things like sheet metal, and many other things that you will use to transform that sheet metal into car, and many other components, all those things. Those are transformed resources. The biggest problem you have when you are looking at transformed resources is how do I make inventory decisions? Because the problem with inventory is inventory has both good parts and bad parts. Inventory comes at cost. It is not free. And somebody has to pay for the cost. But when you manage it well, inventory makes it possible for you to respond to your customer. When you don't have stock, you are not able to respond. But at the same time, when you have too much stock, you are going to be paying for what you don't need that you are keeping. Now, that's one side. We call it transformed resources. And the biggest problem is stock. The second part of every resource you have in any production system, goods or service, is what we call transforming resource. Those are the materials that work on what you are transforming. In the manufacturing of a car, for instance, we're going to have your robots, we're going to have your storehouses, we're going to have your many things.
Yes.
The assembly line that is going to be moving them and all of those things. Those ones, the biggest problem you have with them is not stock, it is capacity.
Okay.
And those two, you can't separate them because what capacity makes is also stock. Now, when we talk about flow, all those materials are flowing through your system. In every case where you have flow and you have capacity constraints, you're also going to start having what we call use. Whether you like it or not, it's like, imagine that a number of you have to go through a place that has a restriction. If many of us have to run through the door has capacity. How many people can go through the door at a time? When many of us are flowing through the door limits us. Then the number going out is not necessarily the number that wants to go out.
Yeah.
So all those things affect what we call flow. So once you have transforming resources, then automatically you are going to have what we call capacity constraints. All those things play together. Those are the things you put together in an integrated manner to say, at what rate should material flow? At what rate should job flow? At what rate should customer flow? When customers are flowing, how does that translate to use? So we have what we call queuing models, simulation models that use to study how those things will emerge because it affects how many you can make at a time. It also helps to also be able to pinpoint what we call bottleneck stages or bottleneck stations, where we tell you if you really want to improve your flow, it's not every station that you invest your money in, because there are some places that when you invest money, you don't get a return. There are places where you invest money in a manufacturing environment, you get return. For instance, a chain, we say is as weak as the weakest point. If you want to break a chain, a smart person doesn't break the strong point of a chain, you break the weak point. And if you want to make a chain strong, you don't make a strong point stronger when there are weaker points. You first make this weaker point strong. Because the weakest point is what determines whether your chain will break or not. That's one of the fundamental thinking in what we call synchronous manufacturing or theory of constraint. So all those things about flow is about materials going through the system. And how do we study how flows build up, how queues build up, how entities flow, which now affects your throughput rate, which automatically also affects your throughput cost, the unit cost of the processed product at the end of the day, and all those things are modeled. So flow in that case means how the transformed resources go through your system and how you control them.
All right, thank you very much, Prof. I mean, we're running out of time, so but I need you to touch on this. You've understudied the industrial system in Africa. What are the skill gaps that you've noticed, and what do you think, or how can maybe either governments or schools like universities can help to cover those gaps so that we can get better manufacturing industries?
Okay, maybe I will start from my field. That's why I started by saying actually the first thing is people don't even understand what industrial engineers do. Because by the time we understand that, we'll see how some small changes can make significant impact in our output when we start talking about skills. Let me start from that. Let me give you another story. If you look at what happens in Japan, after World War II, Japan was a very poor country. Their infrastructure has completely collapsed. Now, look at Japan from after the Second World War in the 1950s and now. Look at all the cars you have on the road. Can you see how many of them are Japanese cars? And you start asking yourself, what did Japan do to transform themselves between then and now? They didn't have better machines than what we have in the western part of the world. Is that not correct?
Yeah.
But what did they do? That they took over almost the whole market. It is not about the technology per se. It's about how the technology is used. That is part of what we call production control. Look at, and you can see that across many countries that are growing, that they need to pay attention not only to acquisition of technology, but how you put technology to work. That's what you design in a place like industrial engineering. Now, this is what I'm going to say. If I were to advise the government, there is a very brilliant idea that the government did in the days of people in southwestern Nigeria, in the days of very smart people like Chief Awolowo. There are things that you give to the people to do. There are some responsibilities I will advise that the government should take over from them. For instance, they started something called farm settlements. I will tell you how it works. They know it's very expensive for every small farmer in the southwestern Nigeria to buy tractors, to buy plows, mold balls, and buy all those things. What did the government do? They took over those things and absorbed them into the Ministry of Agriculture. Then they gave the people land. Then the government got those implements that are expensive, but they created a schedule where the machine can help people to work and they can recover the money from what the people were doing. So the government can keep sustaining that system and the people are reaping benefits. So the people don't need to own the tractor, but they could have the benefits of big farmers that own tractors. That's a very smart idea. We have many things we can do in the industry. For instance, many of those small, one of the things that have been known, that have been studied in today's world is small businesses that make economy grow fastest.
Yes.
And if you want money to quickly get to the grassroots, is money from the small businesses that get quickly to the grassroots. The government that is serious in getting people out of poverty quickly and getting them rich quickly will invest in how they can bring small business out of quickly. And part of what I will advise is that template of what do you call it now? Farm settlement structure is a beautiful thing. We can have industrial, for want of words, industrial settlement system. For instance, I will tell you some big investments that those small businesses cannot have, whether it's manufacturing or service. They can't, it's very expensive. And you need it in today's world. For instance, many of those big businesses cannot afford good enterprise systems to connect them. To buy systems like Oracle, SAP is very expensive. But you need such systems to plug into the world of today and to manage your business and have a view of what is going on everywhere. Nothing says the government cannot invest in that and bring those companies in. And so we take this responsibility for you. You do what you can do well. What you can do is make hair cream. Make your hair cream. We will onboard you. What you can do is make small manufacturing thing. Make it, we will onboard you. So that all those complex things that are difficult, that once you start doing it, you have to forget about what you are doing properly. We will take them away from you. Another thing is, many of those things about analyzing process, these companies cannot have the capability. Many of them cannot afford to hire an industrial engineer. It's expensive if you really get a skilled one. So what happens therefore, those are things the government can invest in and say, can we create such industrial or productivity park through which we are going to onboard many of our small businesses? And then that makes the profit of productivity to filter down to the grassroots very quickly. That would be a very smart idea.
Oh, thank you so much, Professor. I like I said, I anticipated all these nuggets. We're going to bring you back again another time because we have unfinished business. But thank you so much, Professor, for coming in today. Professor Adetunji emphasizes that Africa's industrial growth depends not only on just investments in machinery, but also in intelligent process designs, workforce, and of course, capability. Thank you so much, Professor, for joining us today on Just Africa. Until next time, I will see you again.
Thank you. Thank you for having me. I appreciate it.
Thank you so much.
You must have a good day.
All
Bye.
Right, all right.
Bye, sir.